My calculator says that 10 raised to the power of 3.581 is about 3,810. Super. I could rewrite this as a statement about logarithms. It's saying the power of 10 that gives the answer 3,810 is about this, 3.581. Super. And I go backwards. Let me start with a statement about logarithms. My calculator says, for example, the logarithm base 10 of 103,041 is about 4.013. Fine. And I could rewrite that as a statement about powers of 10. 4.013 is the power of 10 that gives that answer. So if I use 4.013 as a power of 10, I should get this answer, or thereabouts. Okay, super. We go back and forth between statements of logarithms and powers of 10 and logarithms. Grand and good. But of course, back in the day, Napier's day, in the 1500s, 1600s, Napier did not realize that his logarithms were just actually powers of 10, powers in disguise. Nonetheless, his method said, his approach said, we can turn multiplication problems into addition problems nonetheless. And he was right. He was absolutely right. And I want to explain today, see if we can figure out today, why does Napier's logarithms turn addition problems, multiplication problems into addition problems? So I'm going to use the examples here. Napier said something like this. If you wanted to work out, say, well, the numbers I've got, 3810 times 103041, he says, go to my tables and look up the first logarithm value, the logarithm of the value of the first number, the logarithm of the second number, and then add these. Adding these is going to be the key for you. What's the addition of that? That's 7.594. Apparently, the summing these two log values is going to be the key for you. All right, all right. From a modern day perspective, we say, okay, now that we know that logarithms are really just powers in disguise, we could say, all right, 3810 is really this power of 10 in disguise, 10 to the 3.581, times this number, which is really 10 to the 0.4013 in disguise. All right, that's our modern day perspective. We realize these are just powers in disguise. Oh, but I know an exponent rule. 10 to one power times 10 to another power, you just add the exponents. There it is. We're adding these exponents. That's exactly what Napier wanted us to do. 7.594. All right. And then people say, okay, I need to know what number has logarithm equal to 7.594. They go back to Napier's tables and look up logarithm of what equals this answer. We can do this on a calculator. I did on a calculator, and I got something like, I need my glasses. What did I get? Some great big number. 3926494. And I bet that's pretty close to the actual product of these two original numbers. I'm sure there's some rounding going on because I rounded to 3 decimal places everywhere, but there it is. Okay, that's how we would turn multiplication problems into addition problems. That's what Napier wanted us to do, and he was right. He was absolutely right. We can now see it's really this exponent rule that made his method work. So let me be very explicit about that exponent rule and its connection to logarithms, because many people like to write a specific log rule based on that, which sounds scary, but it really is just this idea made to look scarier, I guess. All right, okay, so what's the basic exponent rule I used just then that makes Napier's theory work so beautifully? Well, it's this one. A power of b times another power of b, so the same bases, two different exponents, b to the n times b to the m. The rule is you just add the exponents. It's b to the n plus m. We know that from our work on exponents. So what I want to do is actually translate that into a statement about logarithms. Now I've got logarithm base b. I did base 10 earlier, but I'll do logarithm base b. I can say the logarithm base b of this product, b to the n times b to the m, is really the logarithm base b of b to the n plus m. After all, this product is b to the n plus m. And think about this. What's this saying? It's asking for the power of b that gives that. Well, clearly, n plus m is the power of b that gives the answer b to the n plus m. This is n plus m. It's one of those tautological things again. It makes your brain hurt. N plus m is the power of b that gives the answer b to the n plus m. Whoa. So that's basically it. That's the fundamental log rule people like. But they like to rewrite it, make it look a little friendlier here. Because that looks weird. That looks weird. Well, I guess that looks fine. But people say, okay, no, let's make this look a little bit easier on your eyes. Let's call b to the n a name. Let's call b to the n, I know, big N. And let's call b to the m big M. All right. And to go back to little n, I can say, this tells me n is the power of b that gives the answer big N. So it says n is the power of b that gives big N. And it says m is the power of b that gives big M. All right, so we'll use this notation instead. And my technique on the board is getting pretty terrible, so let me change colors yet again. Let me just rewrite what's in this box using this notation. We have in the box that log base b of b to the n, that's n, big N, times b to the m, that's big M. Log base b of n times m, the product of two big numbers, is little n plus little m. Little n plus little m is log base b of big N plus log base b of big M. There it is. That's how people like to express Napier's dream, that logarithms turn a multiplication problem into an addition problem. There's a fundamental log rule, as many books like to call it. So let me just rewrite that again. One great big line. It's really just the exponent rule I've just erased. I should have erased what I just wrote on the board there, but in the end, we have the logarithm of a product, b times m is the sum of the logarithms. And it's really just me, m. It's me just doing b to the n, b to the m equals b to the n plus m quickly on the side. That's where it really is coming from. All right. So let's have fun with this. Let me just do a little example. On my calculator, logarithm, I've got it written out, the log base 10 of 75 is about 1.875. All right. And on my calculator, log base 10 of 7500 is about 3.875. All right. If I look at that and say, the decimal part's exactly the same. This just went up by 2, Should it make sense that the logarithm of 7500 is just 2 more than the logarithm of 75? And the answer is yes, because of this rule. Look at this. Log base 10 of 7500 is really log base 10 of 75 times 100. That is really log base 10 of 75 plus log base 10 of 100. That is the power of 10 that gives the answer 75. There it is, 1.875, plus the power of 10 that gives the answer 100, plus 2. Yes, if I multiply a number by 100, I can see its logarithmic value should be up by 2. There it is. It's just the exponent rules in disguise, phrased in terms of logarithms. That's how people use this rule. This is how people express it in many books and so forth. And that is actually Napier's dream, consolidated in one statement right there. Napier was brilliant and right. And if he saw their exponents from the get-go, he would have been much quicker getting there. But, that's the nature of the human story.